Hello, welcome to this lesson on the key properties of ionic compounds. We're going to talk about ionic compounds and the types of bonds that they form. We're also going to look at some of their properties and then how to identify them using the periodic table groups and families. So one of the things when I teach this in class that I love to do is go over this awesome video on pool chemistry, and specifically focusing on sodium hypochlorite, which is one of the compounds used to disinfect pools. If you're interested to learn more on that, there's an awesome video from the Reactions channel on YouTube called Is It Okay to Pee in the Pool? Might shock you, some of the things that you'll learn in there. If we take a look at the structure of sodium hypochlorite, we have to figure out first, is it an element, a compound, a homogeneous mixture, or a heterogeneous mixture? So to do that, we first need to review our definitions. An element is only one type of atom. So if we know that an element is one type of atom, a compound is made up of more than one type of atom or element. So if we look here, I see three different elements in there, and I see sodium, oxygen, and chlorine. But the way the oxygen and chlorine are represented is interesting. They've got this line in between here, meaning they are bonded together. And then on the outside, they also have this charge here. What this refers to is something called a polyatomic ion. We're going to address polyatomic ions a little bit later on in this unit, but they essentially function as a negatively charged particle. Just like any other negatively charged single atom, they essentially function the same way. That being said, sodium hypochlorite is definitely a compound because it has at least two types of atoms in there. There's a really great video, actually, another great video that spends some time showing what an ionic bond is. It talks about the electrostatic attractions between the atoms. It shows how the ions are forming. One of the things it does, it uses an animation to show the Bohr model. The Bohr model is the one that was just pictured here a second ago, where you've got different rings around the atom with the different energy levels, and then the outermost energy level is your valence electrons. So in magnesium here, both of these are showing a full set of valence electrons, which means they are different from what their natural states are. The only set of elements that has a full valence shell are your noble gases. Otherwise, some sort of electron transfer has to occur in order to attain a full valence shell. So in that video, what's really cool, they show that transfer. In this particular one, we look at sodium. Sodium has 11 electrons total because there's 11 protons. There's 2 in the first energy level, 8 in the second energy level, and then just 1 valence electron in the outer energy level. When we look at chlorine, chlorine has 17 electrons. It's got 2 in the first energy level, 8 in the second, and 7 in the last level. So when you talk about ion formation, we want to think about what's the easiest thing for the atom to do. I can either lose all the valence electrons I have, or I can gain enough to get to 8. So with sodium, I can either lose the one that I have or add 7 more. With chlorine, I can lose the 7 that I have or gain 1 more. It's way easier to lose 1 if I'm a sodium atom than it is to gain 7 more electrons. If I'm a chlorine atom, it's way easier to gain 1. The thing is, where are they gaining them from? They're not just popping up out of thin air, right? They're coming from each other. There's a transfer that has to occur here. So a transfer of an electron from sodium to chlorine occurs. And what you'll notice is this third ring on the sodium atom disappears. It's gone. That's because there's no electrons in that outer shell anymore. The shell below, which previously had 8 valence electrons, is the new highest energy level, and that is stable because we've completed our octet. Chlorine kept its third ring, it just added one more, and now its third energy level is entirely filled. As a result of gaining an electron, remember electrons have a negative charge. By gaining one, I end up with a 1- charge for chlorine. By losing one, I end up with a 1+ charge for sodium. So to recap, ions form when different atoms exchange electrons to fill their outer energy shells or their valence shells. An ionic bond is an electrostatic force. That was mentioned in the video, but if you're unsure what that means, essentially that is the idea that opposites attract, right? We have opposite charges that are attracting each other here. So opposites are attracting, and that's what holds each other together. You have a positive cation and a negative anion that come close in proximity to each other. They transfer electrons, and they essentially stick together, just like static electricity causes your hair to stick to a balloon and vice versa. Normally, cations are metals of some sort, and anions are nonmetals. And I'll talk a little bit more about that in a minute. In terms of their properties, ionic compounds are solids at room temperature because the electrostatic forces are strong. Because they're strong, they don't melt very easily. A lot of them take thousands of degrees Celsius to melt. And as a result of their strong attractions, they start forming this network of alternating positive and negative ions. And so they arrange in an ordered pattern. That ordered pattern typically is referred to as a crystal or a crystalline lattice, crystal lattice. All those terms essentially are the same. And if you look down here, that's essentially what that is. That's alternating network where you see chlorine, sodium, etc. Even though it's a strong attraction between those things, when they come in contact with water, most ionic compounds are soluble. They can dissolve in water. The attractions that water has for those ions is more energetically favorable, and therefore they will split apart those ions and they will become solvated or dissolve. If we're using the periodic table to help us figure out whether or not something will form an ionic bond, we want to really look at this key feature on the periodic table, the staircase or the steps. For the most part, anything to the left of the periodic table is generally considered a metal. And if it's a metal, it will lose electrons to form a positive cation. The one exception there, I'm going to use a different color to highlight that, is hydrogen. Hydrogen is over here because it's got one valence electron, but it is actually considered a nonmetal. So all these ones I'm shading in right now are nonmetals. And nonmetals typically form anions. The noble gases are also nonmetals, but they don't form anions or cations because they already have their full valence shell, so that's why I did not highlight them, but they are still considered anions. Everything pretty much in these first two columns, your alkali metals and your alkaline earth metals, in addition to your transition metals, all of those things tend to lose electrons so that they can form cations, and same goes for a lot of the elements down here. This bottom row, those are things that are fairly unstable. A lot of them only exist for small periods of time, so we usually won't see anything forming ions down there, but generally this area is considered the transition metals. So that's something to be on the lookout for. So again, if you're forming an ionic bond, there's two ways we can identify if something is going to form an ionic bond. One, if it's a metal bonding with a nonmetal, typically that is an ionic bond. You have to have at least one of each. So if I had lithium, which is a metal, and sulfur, which is a nonmetal, that would be a good candidate for an ionic bond. If you don't have a periodic table and can't look at the locations, if you at least know the charges, you could figure out if it's going to form an ionic bond, because again, opposites attract. So if, say, I had magnesium, which is a +2 charge, and I had chlorine, which is a -1 charge, those are opposite charges. They are going to form an ionic bond. Now, what we'll talk about in a later lesson is how these charges have to balance out. If you add them together currently, we're not going to end up with a neutral ionic compound. So we have to figure out how we can adjust to make it neutral. And that will be the topic of our next lesson. All right. See you next time.